All right, so we're going to go over polynomial functions. And some of this stuff is review from college algebra. The new stuff is going to be how to graph polynomial functions by hand using zeros and their multiplicity. So for a review, a polynomial function of degree n is a function of the form Pn of x equals an x to the n plus an minus 1 x to the n minus 1 and so forth, where n is a non-negative integer. So you can't have that n is like a half or -3. And an is not 0. The numbers, recall that these numbers an minus 1, whatever the variable is multiplied by, they're called the coefficients. The number a0 is the constant coefficient or the constant term. And then the number an is the leading coefficient. And the whole an times x to the n, so this term with the highest exponent is the leading term. This is going to play a very important role, being able to identify what is the leading term and what is the leading coefficient. Is it positive or is it negative? So for example, if I have this function f of x, is this a polynomial function? Yes, because the exponents are non-negative. Yes. Yes, of degree 4. What are the coefficients of the polynomial? So the coefficients are whatever the variables are multiplied by. So coefficients are -3, and then 2, and then there's no x squared. So you can think about its coefficient being 0, and then the coefficient for x is 1, and then the constant term or the constant coefficient is 1. So what is the constant term? Is 1. It's this one right here. What is the leading coefficient? The leading coefficient is -3 here. And what is the leading term? It's this whole thing, -3x to the 4th. The reason this is important is because this polynomial, -3x to the 4th plus 2x cubed plus x plus 1, is going to behave like -3x to the 4th in the long run. So if you recall, this is a power function, and if we let x go to infinity and go to -infinity, so if we look in the long run, the polynomial is going to behave like this power function. Okay, so graphs of polynomial functions are smooth curves with no breaks or corners. So they are stuff like that, smooth curves. They have no breaks, so it can't be like this with a break in between, or sharp corners or cusps and stuff like that. So they have to be smooth curves. Example of graphs of monomials. So monomial is a polynomial made up of one single term. So this is y equals x, and you know this is just a linear. So a linear function is a polynomial of degree 1. And then y equals x squared, you have your quadratic, and so a quadratic is a polynomial of degree 2. And then you have your cubic, is like this, your quartic, so to the 4th power. If you look at x squared and x to the 4th, you see that the shape is similar. The only difference is that x to the 4th is going to be flatter at the origin. See? And similarly, if you look at x to the 5th and x to the, this is x to the 5th. I'm sorry if you can't trying to zoom in. Well, you guys should have the notes and see exactly what this is. So x cubed and x to the fifth. X to the fifth is flatter at the origin. So this is important to kind of have in mind, because when we graph polynomial functions, all the polynomial functions are going to behave like these ones in the long run. But they're not going to look like this. The greater the degree of the polynomial, the more complicated its graph can be. So the domain of a polynomial function is the set of all real numbers, but we're only going to be able to sketch a small portion of the graph. So in order to draw a graph of a polynomial function, we must take into consideration its intercepts. So the x-intercepts, which we also call zeros or roots of the polynomial. We're going to take into consideration its end behavior and its turning point. So we will talk about these individually next. So what is the end behavior of a polynomial function? The end behavior of a polynomial is a description of what happens as x becomes large in the positive or in the negative direction. So if you recall from power functions, we talked about this before. As x becomes large in the positive means as x arrow infinity. So as x goes to infinity, or as x becomes large in the positive direction. We're going to notate this with x arrow infinity. And then as x goes to negative infinity, we're going to denote this with x arrow negative infinity. So, what is the end behavior of a polynomial? The end behavior of a polynomial is given by the leading term. So basically, if I have a polynomial, this should say p1 of x. p1 of x equals negative 2x to the fourth plus 3x plus 1. The end behavior of p1 is given by the leading term. Which is negative 2x to the fourth. So, this polynomial, in the end, if I let x go to infinity and x go to negative infinity, is going to behave like negative 2x to the fourth. So x to the fourth is like this, right? And this is when the leading coefficient is 1. If the leading coefficient is negative 2, if you recall from power functions, the leading coefficient being negative, it just means that I flip this over the x-axis. So what's going to happen, for example, this is going to be negative 2x to the fourth. So even though this has these extra terms, if I zoom out, so as x goes to infinity, for example, as x goes to infinity, where is the y value going? So if x is here, the y is right here. If x is right here, so if I let x increase, the y value is going to be somewhere down here. So if x goes to infinity, the y value is somewhere down to negative infinity. So how do we write this? As x goes to infinity, the y value goes to negative infinity. Now, if I let x go to negative infinity, so if x is right here, y is here, if I let x grow even more in the negative direction, the y is going to be somewhere down here. So as x goes to negative infinity, y also goes to negative infinity. So we say that the end behavior P1 of x is going to behave just like the power function negative 2x to the fourth. And when we inspect that, as x goes to infinity, the graph goes down to negative infinity. And as x goes to negative infinity, it also goes down. So we say that the end behavior of this function is like this. In the end, when x goes to infinity, what does the function doing? Or when x goes to negative infinity, what is the function going to do? So this graph is not the graph of this. Like in between, like in this portion right here, might not be the case. It's not the case, actually. We'll see when we graph polynomial functions exactly. What about P2, the end behavior of P2? Well, P2 is going to behave like 5x to the fifth. And 5x to the fifth, well, x to the fifth, I know it's like x cubed, but flatter at the origin. So it's going to behave like this. So now let's see what happens. As x, if x is here, y is right here. If x grows even more, it's going to be right here. If x goes to infinity, where's the graph? Y going to go? Well, as x goes to infinity, it looks like the y is also going to go to infinity. What about on the other side? If I let x be going to negative infinity. So I notice if x is here, the y is here. If x is here, the y is going to be somewhere down here. And if I let x go to negative infinity, the y is going to be somewhere down to negative infinity. So as x goes to negative infinity, the y also goes to negative infinity. So this is the end behavior of P2. All right. So we're going to need to know what is the end behavior of a polynomial function in order to graph it. This is going to help us. Then another important fact that is going to help us graph polynomial function is a turning point. So a turning point of a polynomial function is going to occur when the graph changes from increasing to decreasing or from decreasing to increasing. Turning points are associated with local maxima or local minima on a graph. So you can think of a turning point as either a hill or a valley like that, or just bumps. So the important thing that turning points are giving us, the important information they're going to give us, is information about the degree of the function. So it's possible to use the graph of a polynomial function to get a lower estimate of the degree of the polynomial. What does it mean, a lower estimate? It's like, what is the minimum degree of this polynomial? If, for example, I have two turning points. See, the function is increasing, and then it's decreasing, and then it's increasing. So there are two places where it changes from increasing to decreasing, or from decreasing to increasing. So there are two turning points. So two turning points means that the minimum degree of this is 3. Okay? So minimum degree is 3. So you add 1 to the number of turning points. Similarly for this one, let's see how many turning points we have. Well, we have a bump right here, and then a bump here, and then a bump here, and then a bump here. So we have 4 turning points. So this means that the degree of this polynomial graphed right here, the minimum degree is 5. The number of turning points plus 1. So the number of turning points tells us the smallest possible degree of the polynomial. So the polynomial on the left must have at least 2 plus 1, which is 3 degree, and the one on the right must be at least 5 degree. So in general, so this is what you should take from here. In general, if the graph of a polynomial has n turning points, the polynomial's degree is at least n plus 1. So you are familiar with this. If you think of a line, there is no turning points in here, so there is 0 turning points. But you know that the degree of a line is 1, so the degree is 1. So in this case, this is exact. This formula gives you exact degree. And for a parabola, how many turning points do we have? 1. So the degree of a parabola is 1 plus 1, which is 2. So 1 turning point. Degree 2. It's not always the exactest formula, so keep in mind that it just gives you a lower estimate. So for example, this polynomial right here has 1 turning point, so its degree is at least 2, but in fact the degree of this one is 4. This is this one right here, where the degree is 4 because it's flatter at the origin. So the fact that it has a certain amount of turning points can just help you decide what's the minimum degree of the polynomial that it's graphed.